Hello everyone, this is Satsandeep from Vignans Nirula, working as assistant professor in CSE department. So today we are going to talk about the applications of linked list. So there are numerous number of applications of linked list. So which starts from your music player, which can go to the previous track and next track using the linked list, and also your web browser if you are using, so it can navigate through the pages, previous page and back page like that. And it can be go through the sophisticated applications like your dictionary service, which can be used for searching more efficiently. And this particular data structure, that is linked list, used to implement other data structures like stacks, queues and trees as well. So let us see some of the applications of data structures in this lecture. Topics covered in this lecture. Here we first start with the addition of polynomials. So we are going to take two polynomials and we are going to add that, and we are going to represent the same thing using linked list. And later we are going to see the multiplication of the polynomials, and after that we are going to see the sparse matrix, means we are going to represent the sparse matrix using linked list. And finally we are going to talk about the advantages and disadvantages that we have with the linked list. Polynomial representation. See, before the addition of these two polynomials, let us see how a polynomial can be represented using linked list. So basically, if you take any polynomial, every polynomial contains terms, and each term contains the two parts. So one is coefficient and exponent. So basically, coefficient is the one which is just before the x, and exponent is nothing but the power of the particular x. So if you take 5x square, so 5 is the coefficient and 2 is the exponent. And now let us see the node structure of the of this particular term. So if we want to represent the polynomial using linked list, we need to have a different node. So let us see. So if you see here, this is the node structure. So every node contains three parts. The first one is the coefficient, so which stores the coefficient of that particular term. The next one is the exponent, so which stores the exponent of that particular term, and next one is the next, so which actually goes to the, which links to the next term. Okay, so if you see this example, so in this example the above expression is actually represented using linked list. So here the above expression, if you see here, so that expression contains different terms, and each term is individually represented using one node of the linked list, like what you have seen now. Next, we are going to talk about adding two polynomials. So when we want to add two polynomials, so first of all what we are going to do is we are going to take two polynomials, and here we are going to compare each term of the polynomial to the first term of the second polynomial. During the comparison, we are going to see the exponents. So if the exponents are similar, so then what we are going to do, we are going to add the coefficients. And if the exponents are not similar, so then what we are going to do, we are going to copy the term to the resultant polynomial. So there are only two things here. So one, if the exponents are same, we are going to add up the coefficients, and if the exponents are not same, we are going to copy the term to the resultant polynomial. If you see here, the first polynomial contains 5x square. So you have only one x square term here. So the second polynomial doesn't have any x square term. So what we are going to do, we are going to directly copy that 5x square to the result. So if you see compare the next two terms of these polynomials, so you have the same exponent. So that is 1. So 5x plus 4x, so we have to add up the coefficients, that is 5 plus 4, which results the 9. Let us see the algorithm for addition of two polynomials. So here we have two polynomials, 5x cube plus 2x square plus 4, that has to be added with 8x square plus 10x plus 3. So both of these two polynomials have three terms each, and initially we have to represent these polynomials in a linked list fashion. So the first polynomial is like this, if it is represented, and the second polynomial is like this. Okay, and now we have to add up these two polynomials, okay, which is in the form of linked list, which forms the resultant polynomial like this. So now let us see, let us trace this using the algorithm for addition. So let P and Q are the two linked lists. So here the P and Q are two linked lists. Set P and Q point to the first two nodes of the linked list. So P is the first node's header node, means the first node of this first linked list is represented by P and the first node of this is represented by Q. So now initialized R linked list R as a first for storing the result. So this linked list R, so initially it is empty, so this is used for storing the result. So now we are going to repeat this step 3. So this step 3 is repeated until P is null and Q is null. So why P is null and Q is null means, so here every time we are going to traverse this P and Q. So here every time we are going to check the exponent of P and exponent of Q. So here how long we can do, either P becomes null or Q becomes null. So we are going to terminate this. So that's why we put AND condition here and statement here before between these two. So let us see. So P is not null and Q is initially not null. So here if P2 exponent is greater than Q2 exponent. So here the point here is, if the exponents are same, then we are going to add up the coefficients, okay, when it comes to the addition of two polynomials. So let us see. So P2 exponent is 3. Is greater than Q2 exponent? Yes, it is greater than Q2 exponent. So now what we have to do? So we have to take a new node like this, and for this new node we have to copy this P value. So what we are going to do? So new node to coefficient equal to P2 coefficient. So new node to coefficient equal to P2 coefficient, and new node to exponent equal to P2 exponent. New node to exponent equal to P2 exponent. Okay. So simply what we are going to do? We are going to copy these values to the new node, and after this what we have to do? Then insert the new node at the end of the list R. Initially there is no list R, so this node will be the new list, okay, R, pointing by R. So now after this what we have to do? We have to, okay, compare these two nodes. For this what we have to do? So this P has to be moved to this one. So P is equal to P2 link. So P becomes this node, okay. And now let us do the same thing again. So is P null and Q null? No. So now is P2 exponent is greater than Q2 exponent? No. So it goes to the else part. So is Q2 exponent is greater than P2 exponent? Q2 exponent is not greater than P2 exponent. No, here P2 exponent equal to, means it goes to the else part, P2 exponent equal to Q2 exponent. So here if you see here, P2 exponent equal to Q2 exponent. In this case what we are going to do? We are going to sum up the coefficient. So coefficient R, new node to coefficient is equal to P2 coefficient plus Q2 coefficient. 8 plus 2 is 10, like this. So that's what we have. New node to coefficient equal to P2 coefficient plus Q2 coefficient, and new node to exponent equal to any one of these two fellows exponent. So it can be either P's exponent or Q's exponent, because both are same, so we can take any one of this. So here new nodes to exponent equal to P2 exponent, so this one's exponent, so like that. And after this, so this time what we have to do? So we put this new node to the end of the previous linked list R, so end of this. So after this we need to move this pointer, so both P and as well as Q has to be moved. P is equal to P2 link and Q is equal to Q2 link. So P now will be here and Q now will be here, and now we'll compare these two. So is P2 exponent, so P is not null and Q is not null, so P2 exponent is greater than Q2 exponent? No. We go to the else part. Q2 exponent is greater than P2 exponent. Now this time Q2 exponent is 1 is greater than P2 exponent, that is 0. So now what we have to do? We have to copy this node to the new node. So it is nothing but nu naught to coefficient equal to q2 coefficient, nu naught to coefficient equal to q2 coefficient, and nu naught to exponent equal to q2 exponent. So nu naught to exponent equal to q2 exponent, like this. Okay, after this what we have to do? Since we have processed only this node, we need to move to the next node this way. So q becomes q2 next, and this new node has to be inserted to the previous list of OR. Okay, so the p and q will be here, and this time p2 exponent equal to q2 exponent. And now what we are going to do? We are going to sum up these coefficients. So nu naught to coefficient equal to p2 coefficient plus q2 coefficient. So here p2 coefficient plus q2 coefficient, that is 3 plus 4, which is 7, and you can take any one of these exponents. So p2 exponent, so nu naught to exponent equal to p2 exponent, 0. So now we have to move both of them. If I move both of them, so b becomes null, and as well as q also becomes null, right? So, and now this loop exits. Okay, so now what we have to do is, see, sometimes what happens, you have very few terms in the first expression and very many terms in the second expression. So what happens? By the term the first expression, the second expression completes, the first expression is already null. Okay, p becomes null. So that time what we have to do? We have to copy the remaining terms of this q to the linked list resultant linked list. Same is the way opposite. Means suppose if we have the terms of p, okay, which are left over, so and the terms of q is already done, so q becomes null, and still there are some more nodes in p. So that time, so you have to copy the remaining terms of p into the linked list. So that's we are going to do in step 4. So copy the remaining nodes if any. If p is null, okay, if p becomes null, so then what you are going to do? So you are going to copy the remaining terms of, if q is null, so copy the remaining terms of p onto the resultant linked list R. So if q becomes null, okay, if q becomes null, and copy the remaining terms of p onto the resultant linked list R. So this is the resultant linked list R, which is the sum of these two linked lists. So if I write this, what happens? 5x cube plus 10x square plus 10x plus 7. So this is the resultant polynomial after adding these two polynomials. Multiplication of polynomials. So the multiplication of polynomials is different from the addition. So when it comes to the multiplication, so if you have two polynomials, so the first term of the first polynomial has to be multiplied with each and every term of the second polynomial. So likewise, the second term is multiplied by each and every term. So every term of the first polynomial has to be multiplied by every term of the second polynomial. So here during multiplication, so here if we have to multiply two terms, so first of all let us see the coefficient part. So if the coefficient parts, if you have coefficients, the coefficients of the two terms must be multiplied, so to the result. And if that is exponent, exponents must be added to the result. Okay, so here after the multiplication, so the term which you have obtained has to be added back to the result. So in the result, if you have the same exponent as the obtained term's result, so then you have to add it to the previous result. So this is how we are going to multiply this is the logic behind multiplication of the polynomials. So this is the example how you take these two polynomials, and the first polynomial have each and every term of the first polynomial must be multiplied with all the terms in the second polynomial. Likewise, so you will be having many terms, and again these terms, if the exponents are similar, this must be added and finally resulting the resultant polynomial. Let us see the multiplication of the polynomials. So here is the algorithm for multiplication of the two polynomials. So here there are two polynomials that are given. So 3x square plus 5x plus 6 and 6x plus 8, and first polynomial have 3 terms and the second polynomial have only 2 terms. So now we need to multiply these two polynomials. So in order to multiply these two polynomials, what we are going to do? So for every term of this first polynomial, we are going to multiply with that with the second, with all the terms in the second polynomial. For every term of the first polynomial, we are going to multiply with all the terms in the second polynomial. So now what, every time you multiply, you will get the product. So once you get the product, so you are going to compare with the previous product's coefficient, exponent, and if the exponents are similar, so then what, you are going to add that with the previous coefficient. So let us see how it runs. Okay, so here basically we won't check for any coefficients and exponents, we simply multiply. While multiplying, what we are going to do? So if the coefficients, if you have coefficients, the resultant polynomial's coefficient is nothing but sum of the resultant polynomial's exponent is nothing but sum of the exponents of the polynomials, and the coefficient is nothing but the product. Okay, so let us see. So the same way here, P and Q are the two linked lists. So P is represented by the first node in the first linked list, and Q is represented by the second node in the second linked list. And initialize the linked list R. So R is initialized, and now we are going to repeat this step 3. So here only we have only 4 steps. So in step 3, while P becomes null, okay, so you are going to repeat this loop. Okay, so initially P is not null, so it go inside. So in this we have another loop, so which is Q. So is Q is null? No, Q is not null. So now we go inside this. So what, every time what we are going to do? So this is the new node. So new node to exponent. Exponent is equal to P2 exponent plus Q2 exponent. So here 2 plus 1 is equal to 3. Okay, new node to exponent equal to P2 exponent plus Q2 exponent, and new node to coefficient is equal to P2 coefficient plus Q2, P2 coefficient into Q2 coefficient. So 3 into 6, 18. Okay, after that, so you have to move Q is equal to Q2 link. Q becomes this, and again you have to multiply this node with this node. Okay, okay, now if you want to multiply these two nodes, okay, P is here and Q is here, and now what we want to do here? So we want to multiply these two nodes, and if we want to multiply these two nodes into the new node, so let us see how it happens. So the new node to exponent, so new node to exponent is nothing but P2 exponent, which is 2, plus Q2 exponent. 2 plus 0 is what? 2. And new node to coefficient is nothing but, new node to coefficient, this value is nothing but P2 coefficient, which is 3, into Q2 coefficient, which is 8. 3 8s 24. So 24 will be the coefficient of that result. Okay, so this creates a node which contains 24, 2. Okay, and it will be added to the previous linked list. Okay, so and now Q is equal to Q2 null. So if Q is equal to Q2 null, what happens? Q becomes null. So if Q becomes null, what happens? This while loop exits, because this while loop continues until Q not null. So once Q null, so this while loop exits. So now here what happens? P becomes P2 link. So now P is equal to P2 link. So now this node will be the new P. And now if this node is the new P, okay, so and you are going to again start the Q from here. Okay, because we are going to multiply this each and every term of this Q with this every term of this P. Okay, so let us see. So here, while Q not null, so Q is not null. So now what we are going to do? New node to exponent is equal to, so the new node to exponent is nothing but the exponents, the sum of these two exponents, P2 exponent and Q2 exponent. 1 plus 1 is 2. Okay, 2. And now new node to coefficient is equal to, so 5 P2 coefficient into Q2 coefficient. P2 coefficient is 5 and Q2 coefficient is 6. 5, 6, 30. Okay, so you have 30 and exponent is 2. Okay, so and now this new node has to be added to the previous linked list. if it has to be added to the previous linked list, we have to check whether this coefficient exponent 2 is already exist or not. Yes, it is already exist. The coefficient is 24 and exponent is 2, right? So, and now you have to add the new node to this already existing node. So, now if I add this, so since exponents are same, so 2 and 2 are same, we have to add the coefficient. What is the coefficient here? So 30. 30 is added to the 24, so and it is nothing but 54. Okay. So this is how we are going to, means every time you get the product, so you are going to compare with the existing linked list, and if exponents are similar, for that node you are going to add that coefficient. Okay. So now what happens in the next iteration? So q will be here and it will be multiplied with this node, and q becomes null after, and now after that q will be here and q will be multiplied, sorry, p will be here and p will be multiplied with these two nodes also. Okay. So now after this, okay, so what happens? This is the resultant list. What is the resultant list? 18x cube plus 54x square plus 76x plus 48. Okay. So this is the product of these two polynomials. So before we see how we can represent the sparse matrix, let us see what is multi-linked list. So basically your multi-linked list is one of the forms of your linked list which you have many pointers. So basically if you take a single linked list, it have one pointer, and if you have doubly linked list, it have 2 pointers. But when it comes to the multi-linked list, it can have n pointers. So n can be more than 2 or even 1 or 2 or whatever, depends upon the type of applications. So generally these multi-linked lists are used to represent the different forms of the same list. For example, let us take, if you take a student data set, so every student contains names and marks. So if you want to represent this linked list, and you have to, so if you have this data, so the same data can be represented in 2 ways. So one linked list can be traversed using the alphabetical order, okay, so according to their names in ascending order. So in the other way, so the same list can be represented using by incremental order of their marks, like this, what you are going to see. So here you have 2 linked lists, each and every node have 2 links. So one, if you follow one link, so it will be like it will go along the marks, and if you follow another link, so it will go along the names. Sparse matrix. So basically if you take a normal matrix, so the normal matrix contains the elements which are arranged in a row and column manner. So when it comes to the sparse matrix, it is like your normal matrix, but most of the elements are zeros, okay, and very few elements are non-zero elements. And when it comes to the representation of sparse matrix, so why we have to deal this problem in a different way? Because so when we want to represent the sparse matrix using arrays or any other things, so lot of memory gets wasted. Imagine if your matrix contains 100 elements in which only 2 elements are non-zero elements, so you need to waste 100 memory locations or 98 memory locations in order to store zeros which are of no use. So generally these are used to, these sparse matrix are used to deal the real-time engineering problems, like the digital signal processing, where you have to deal with a huge amount of matrix, huge size matrix, where most of the elements are zeros. In order to store this, we need to have a much more efficient data structure. So now let us see how we can represent this sparse matrix using linked list. Let us see the representation of sparse matrix. So here the sparse matrix can be represented using multi-linked list. So using multi-linked list means each node represents a non-zero element. So you are going to create a node only for the non-zero element. So let us see the node structure for this. So if you see here, representation of sparse matrix. Sparse matrix can be represented using multi-linked list. So here if you take a multi-linked list, it contains nodes, right? So here for representing the sparse matrix, we are going to create the node only for the non-zero element. Okay, so we are not going to create a node for a zeroth element. So here we are only representing the non-zero elements. For that we need a separate node structure. Let us see the node structure. So here the node structure, if you see here, it contains 4 fields. The first field is coordinates. Coordinates is, so if you see here, coordinates is nothing but a particular row in a particular column where the non-zero element present. Okay, next comes the node, the data part. So the node itself, the non-zero element itself. Okay, next in the row is suppose you have a node, and that node have a next node in the particular row. Okay, so it gonna have a link. So this is a particular link to the next node in the row. So the same way you have the next node in the column. So you have another link that links the next node in the column. So using this particular node structure, we can represent the sparse matrix. Okay, let us see the representation of sparse matrix with an example. So if you take this example, so this is the sparse matrix, because most of the terms, means here if you count here 1, 2, 3, 4, 5, 6, 7, 7 are 0 terms and only 4 are non-zero terms. So non-zero values are very less than the 0 values. So this is the sparse matrix. So now if I have to represent this using the linked list, okay, so here first of all what we are going to do here is, so we are going to represent the non-zero elements only. We are going to create a node only for the non-zero elements. Okay, only to represent the non-zero elements. So how the node looks like? So node have 4 fields. So the first one is coordinate, the next one is the data value, and these two are the links. Okay, link to the next column and link to the next row. So let us see. So here first of all we have to represent this non-zero element, that is 25. So 25 is where what are the coordinates of 25? It is available in 0th row and first column. So the coordinate value is 0th row and first column. And what is the value here? We have 25. Okay. So and these link fields we are going to see it later. Okay. First of all we want to fill these two columns, these two. Okay, for each node. So now for second row, okay, which is at index 1, so we don't have any nodes, any non-zero elements. So now if you go to the third row, we have 17 as a non-zero element. It is at, what are the coordinates here? So second row and 0th column. Second row and 0th column you have this node 17. 17 is the value. Same is the way in second row, second column you have 5. Second row, second column you have 5. Okay, so you put here. So this are the row links and these are the column links. Okay, so 0, 1, 2 and 0, 1, 2, 3. Okay, so like this. So now here in the finally the third row, 0th column you have the last element which is 19. Third row and last column we have 19. Okay, once we done this, we have to put these links. So how we are going to put these links is, first of all we start with rows. Okay, linking the rows together. Okay, so here if you see here, we have to check, is there any node in this row? Okay, so we have this node in this row, right? So we directly link this row link to this node. Okay, once we done that, so now we have this as the row link. Okay, this represents the row link, right? So this row link, is this node have any node next to it in the row? So this is the last node. There is no next node for this. That's why we put null here. Okay, so now let us go to this node. Okay, so since there is no node in the second first row, so we go to the second row. In this second row, so as we have nodes here, so we have direct link like this. And for this node, is there any next node in the row? Yes, we have this as the next node for this. So we directly connect this from the, so what is this? Next row. So this next row field to this, okay, like this. Now for this node, is there any next node? No next node. So that's why we put null here. So same is the case here. So here there is no next node for this, so that's why we put null here. So once we have done filling up the rows, okay, row links. Now let us see the column links. So these nodes represent the columns, okay. So this is the 0th column. So let us see, is there any node in the 0th column? Yeah, we have node. This is the first node that we have. So we directly connect this node to the first node of this, like this. And after this, for this represents the column link. So is there any node after this node in the column? Yes, we have this node after this node in the column. So that's why this node means 17 node is connected to 19 node like this. The same is the way like this for this. So this in the column you have one node like this that is connected by this. And now after this we have to check, is there any node after this node in the column? There is no node after this node in the column. That's why we put null in the column field. So same is the case with this node also. Okay, here in this node, after this node, is there any node in the column? So there is no node in the column, so that's why we put null like this. So this way we can represent any number of non-zero elements using the sparse matrix using linked list. Okay, so the only thing is here, how many number of columns you have? So 3. So you have to put three column links. And how many rows you have here? So you have 4. So 4 row links, and now you have to represent the non-zero elements like this, and after doing that you need to interconnect the rows and columns appropriately. So far we have seen the applications of the linked list. So now we are going to see the advantages of linked list. So the first advantage is it is dynamic. So it means that during runtime you can add any number of nodes as you want. It may not be possible with the array. So array is like, once you fix the size of the array, so you can't grow the array afterwards. But when it comes to the linked list, it is not like that. So you can add any number of links on the go. Okay. So the next application is the insertion and deletion. So when it comes to the insertion and deletion, it is very much simple when it comes to the linked list. Let us take the array. So we can compare this with the array because both are linear data structures. So here when it comes to the arrays, so if you want to delete a particular element, so once you delete, you create a room and you need to shift all the elements back. And suppose you want to insert a particular element in middle, so you need to shift all the elements towards right. So it is really complex when it comes to the programming these things. So for the linked list, it is very easy just to, while insertion and deletion, so you simply change the links. The next one is the memory wastage. So here when you take the array, so it takes, once you can't predict how much memory is required, so that you may give a huge amount of space, like say int a of 1000. Suppose you only have used only 100 elements in order to represent. So all the 900 elements get wasted. But when it comes to the linked list, whenever you require a node, you just can dynamically create it. So by that we can reduce the space. So next, implementation. So using this linked list, we can implement other data structures like say stacks and queues in a much more efficient manner. As the linked lists have many advantages, it also comes with its own disadvantages. Let us see the disadvantage that we have with the linked list. So the first disadvantage which we see here is that memory wastage. So here memory wastage is a kind of like, suppose we can compare with the array. So if we want to insert an element in an array, it takes only 1 unit of space. But when it comes to a linked list, you need to create a node for that element. So for creation of that node, it takes 2 parts. So that one is link and as well as the data part. So for every element, it takes 2 units of space rather than 1 unit. So if you take n elements in array, it takes n units of space. when it comes to the linked list, it takes 2n units of space, which wastes a lot of space, right? So the next is the traversal. So traversal is like, suppose when you want a particular node in an array, so you can directly go and access that. But when it comes to the linked list, so you have to start from the first node and you have to reach all the way, you have to visit each and every node, though it is unnecessary. So you need to go to the final node, so which is really costly, okay, compared to arrays. So the next one is the reverse traversal. Reverse traversal is like, see, if you go one way like this, so if you want to go back, so unless it is a doubly linked list, it is not that simple. So you have to again come back, okay, from the starting node, again start traversing that. You cannot go back, okay. Okay, let us have a quick recap of what we have learned today. First, we have seen the polynomial addition. So before that, we have seen how we can represent the polynomial, and also we have seen the algorithm for representing the polynomial. And also the next one, we have seen the polynomial multiplication, and we have seen the algorithm how two polynomials can be multiplied together. And next we have seen how a sparse matrix, what is sparse matrix and what is a multi-linked list, and we have seen how we can represent the sparse matrix using multi-linked list. And finally, we have seen the advantages and disadvantages that we have with the linked list. And so this here I end this lecture. So in the next lecture, we are going to see the doubly linked list. Thank you.